Okay, I think we're ready to get started. Good evening, everyone. Welcome to our sixth Mary Talk of the season. My name is Jeremy Vaughn. I am the Associate Director of Alumni Programs and Director of Arts Advancement here at Mary Washington. It is my pleasure to welcome you to this evening's Mary Talk featuring Pamela Grothe, Assistant Professor of Earth and Environmental Sciences, as she presents COVID-19 and Climate. What impact is the pandemic having on the environment? Tonight's lecture marks our fourth digital presentation of Mary Talks since the pandemic began, and we are excited to welcome all participants of tonight's lecture, which consists of over 300 students, alumni, parents, and friends from across the country. Also worthy of note is an alumna from the graduating class of 1950. Shirley, we're so glad that you're joining us tonight. As with past digital lectures, there will be time after the talk for Dr. Grothe to answer any questions you might have. So keep that in mind as you listen to tonight's presentation. Feel free to write any questions in the comment area to your right, and we'll do our best to get to them. And before we begin, a few words about our presenter. Pamela Grothe earned a Master's of Science in Geology at the University of Colorado and PhD in Paleoclimatology from the Georgia Institute of Technology. Her research uses natural archives to reconstruct the climate hundreds to thousands of years ago in order to create a baseline of natural climate variability so we can better understand humans' contribution on present-day climate. Pamela is also proud to work at her alma mater as an alum of Mary Washington who graduated in 2006. It is now my honor to present tonight's guest. Pam, the floor is yours. Welcome to Mary Talks. Bring you up here.
Hey, thank you. All right. Thank you, Jeremy, and thank you all for joining me today. I was so excited to see that I have former classmates and former students, as well as also some family that are joining us tonight. So thank you again for taking the time to listen to what I have to say tonight. And I think now more than ever, with all that's happening in the world and our country, is the time for us to come together and to keep communicating about climate change, especially because this is another social justice issue that illustrates the disparities in our communities, with so many more African Americans affected by the impacts of climate change. And many of you have probably been hearing in the mainstream media the impacts that the COVID-19 pandemic is having on the climate, with the economy of most of the major countries shut down and people are staying home. In fact, it's actually been quite overwhelming that I've even had a hard time keeping on top of it all as I was preparing for this talk. But we've heard about the clearer skies, the cleaner air, the quieter cities, the reduced emissions around the world during this pandemic. And so during this talk, I want to dive into some of the global, the regional, and even the local environmental impacts due to these massive scale lockdowns. I'm focusing on the impact of climate change. But before I start, I want to preface that not a single environmentalist or a climate scientist would wish such an event as a way to clean our air and to reduce our carbon emissions. So the reduced emissions that I'm going to talk about, they are not from decarbonizing our economy. It's from these forced lockdowns around the world at the consequence of human lives lost and economies paralyzed. So we should not celebrate this. But what I think is that we can learn from this information to help drive policies to reduce pollution and to reduce greenhouse gas emissions as we develop recovery stimulus packages for rebuilding our economy. But I want to first start telling you a little bit about myself. So like Jeremy said, I am an University of Mary Washington alumna and graduated in 2006. And it was my undergraduate experience, research experience here with the late Dr. Neil Tybert, whom some of you may know, where I first became interested in studying the climate. I participated in a summer research experience with him, researching the environmental change over the last several thousand years in the Dominican Republic. And it was that research experience that shaped my future as I decided to pursue my PhD at the Georgia Institute of Technology in paleoclimate. And that's really just a fancy term for saying past climate change. And I really like this quote from Dr. Naomi Levins, who's a professor at the University of Michigan. And she says, "I provide clarity to uncertainty." So as a paleoclimate scientist, I study how the climate varied naturally in the past so that we can put the human-caused climate change in context. So this is a picture of me here on Christmas Island. This is a research site of mine in the middle of the tropical Pacific. And I use the geochemistry from these fossil corals to tell us how ocean temperatures and salinity varied in the past. And in fact, my most recent research even highlights how El Nino events are stronger in the last 30 years compared to any other time over the last 6,000 years. I'm suggesting that these events are sensitive to climate change. And of course, this is a whole nother topic in itself that I'm not going to get into here. But climate change and its impacts, they are making headline news over and over, and especially prior to the pandemic. And it's usually not good news. So here are just a few examples from earlier this year from the New York Times and the BBC News. The Australian bushfires that ravaged 72,000 square miles, destroyed almost 3,000 homes and 6,000 buildings, killing 34 people directly and many more indirectly from poor air quality, and then even displaced billions of animals. Scientists say that bushfire risk is 30 times higher with the extreme prolonged heat that the region is experiencing because of climate change. The UK saw some of its worst floods this winter with record rainfall. The month of February was actually the wettest on record since they began recording rainfall in 1862. News articles on melting of ice sheets are constantly coming out, especially as we get better technology on how to measure those changes. And of course, it seems that every year we are topping the records, with 2019 being the second warmest year on record. But maybe on a better note, Yale's climate change communication did a survey in April during the pandemic and found that the American public opinion about climate change has remained steady throughout the pandemic, and that Americans' understanding that climate change is happening and that it's caused by humans is actually at an all-time high right now. You can see here in these two charts with the green line that 7 out of 10 Americans think that global warming is happening, and 6 out of 10 Americans say that it is human caused. But even though climate change has only more recently been in the spotlight in the news, as more and more scientists are studying it, as we come out with more comprehensive reports that illustrate how dire the situation is and the impacts that we're already feeling and how much worse they're going to become. But the reality is that the science behind human-induced climate change is simple, and we've known about it for almost 2 centuries. I really like this climate milestone timeline. And you can see that the idea of greenhouse gases goes back to 1824, when Joseph Fiore deduced that the atmosphere must be responsible for containing the heat absorbed from the sun, and he coined the term the greenhouse effect. And this was even before we had instrumental temperature records. And then in 1896, Svante Arrhenius, he presented the idea that burning fossil fuels could lead to global warming, and even calculated the warming from a doubling of CO2. And in the 1960s, scientists began warning policymakers about climate change. So without our atmosphere, Earth's temperature would be about 0 degrees Fahrenheit. Instead, our global temperature is a balmy 59 degrees Fahrenheit. And this is because of the greenhouse gases in our atmosphere, which water vapor is the most abundant greenhouse gas, but of course, then there's the carbon dioxide or CO2, and then methane as well. So the sun, it provides energy in the shortwave radiation, which is mostly invisible to the atmosphere. And about 30% of that energy is reflected back to space by things like clouds and ice. Then the Earth absorbs the rest of that energy and then re-emits that back out as long-wave radiation. And so the greenhouse gases, they absorb that long-wave radiation and then they re-emit it back out in all different directions, creating that greenhouse effect. And we can very easily measure the concentration of greenhouse gases, particularly carbon dioxide. So this is me on Christmas Island. I'm collecting an air sample for Scripps Institute of Technology. So this is a glass flask, it's vacuum sealed. I take it and I hold my breath and I face it upwind away from any cars, and then I open it up and you hear a hiss, and then it fills up with air, and then you close it back, and then we send it back to the lab. And between the National Oceanic and Atmospheric Administration, or NOAA, and Scripps, we have these dedicated collection sites all around the world collecting these air samples that are then sent back to the lab to measure the carbon dioxide concentrations. And so the longest and most famous carbon dioxide time series is from Mauna Loa Observatory in Hawaii, and this is called the Keeling curve. So this is a plot of CO2 concentration in parts per million at Mauna Loa, and it goes back to 1958. And there are two trends that you can observe. So first is this oscillating pattern seen in the red line, so this up and down pattern, and that represents the seasonal cycle. So this is driven mostly by the northern hemisphere where there's more land. So in the spring, as plants bloom, they take up the carbon dioxide, lowering the atmospheric values. And then in the winter, as plant matter decays, the CO2 is released back into the atmosphere, raising the values. And second is the long-term trend of ever-increasing values from below 320 parts per million in 1958 to over 415 parts per million today. And this trend is from burning fossil fuels. But really, this is an incredible record as it's a first of its kind that highlights the rising concentration of carbon dioxide in the atmosphere. And we can even zoom in on just the last 4 years. So last April, CO2 concentration was 413 parts per million. This April, CO2 concentration is 416 parts per million. And actually, I just checked prior to this talk, and May was at 417 parts per million. So you can see that the concentration has still gone up over the last year. And on average, the concentration rises by about 2 parts per million a year because of the fossil fuels that we emit. So as a paleoclimate scientist, I always like to put present day into perspective of the past. Scientists are really clever, and we have developed many different measurements to quantify past atmospheric carbon dioxide concentrations. And the most straightforward method uses air bubbles that are trapped in ice, as you can see here in this picture. So they are like little time capsules of ancient air. So snow has lots of air throughout it, and as more and more snow gets compacted, that air gets trapped in those layers and preserved as little bubbles as the snow turns to ice, forming to what we know as our glaciers. And it turns out that this is an extremely accurate measurement. As you can see here, is this plot pairs the carbon dioxide concentrations from the Lal Dome ice core data, which is in Antarctica, with actual atmospheric carbon dioxide, and which is the black line there. And I should note that the carbon dioxide concentration is fairly consistent throughout the atmosphere, meaning that the values that are seen here in the South Pole, they reflect global values. Ice cores go back hundreds of thousands of years. If we first just look at the last several hundred years, we can see this fairly steady rise in CO2 concentrations in the 1800s, and then until you hit that sharp rise around 1950. So just for reference, we usually refer to changes from the pre-industrial, and that concentration was 280 parts per million. We can take this back even farther to the last 10,000 years, a time that we call the Holocene. And you can see fairly constant values again with this slight rise over the last 6,000 years or so. And some would actually argue that that is related to large-scale agriculture that was taking place first in China and then in Europe. But here's where it gets really interesting. So this now extends back 800,000 years. And you can see what we call this sawtooth pattern. So this rapid rise in CO2 followed by a more gradual decline. So periods of higher CO2 concentrations, those are called interglacials, so the warm periods, much like we are in today. And then the lower levels are glacials or ice ages. And what is striking is that you can see that our pre-industrial concentrations are equivalent to the last interglacial concentrations. And in fact, if we were just to leave it alone to natural cycles, we most likely would be headed towards a very slow decline in CO2 to the next glacial period over the next 100,000 years. But if you look, there is no time in the last 800,000 years where CO2 levels were as high as today. We actually have to go back 23 million years ago to see these kinds of levels above 400 parts per million. But we also have to keep in mind that at that time, the rise to those levels were gradual. They were not sharp like today. I mean, you've also seen I've marked our best estimate of when Homo sapiens evolved around 300,000 years ago, and we've managed to live through several glacial and interglacial cycles. And interesting enough is that these cycles are driven by orbital parameters. They're called the Milankovitch cycles. So particularly that 100,000 year time period of going in and out of ice ages is related to how circular or how egg-shaped our orbit is around the sun, which affects the total amount of energy that Earth receives. So here, the CO2 is actually responding to changes in temperature from that change of energy from the sun as carbon is moved mostly back and forth between the ocean and the atmosphere. But as I mentioned, it's well known that carbon dioxide is a greenhouse gas, and it most likely amplified the temperature changes that we're seeing from these glacial to interglacial periods. But today, carbon is almost solely the source of our warming because of that greenhouse effect that I mentioned. When we try to model our historical and present day temperatures, we can't get the right answer unless we add the human factor. This plot here illustrates the temperature changes over the last 100 years, where the green shading just models natural climate factors like sunspots and volcanoes. And you can see that we don't get that temperature spike until we add the human factors from burning fossil fuels, which can be seen as the blue shading here, and that matches the black line, which are observations. So natural climate variability does cause some ups and downs in temperature, but that's it. They're just background noise amongst this long-term trend of rising temperatures. And it seems that almost every year we are breaking the charts in terms of record global temperatures. 2019, which is showing here the global temperatures month by month, that was the second warmest year on record. The last 5 years, they're all the hottest years on record. And if we look at the 10 hottest years on record, they are all since 2005. And what is alarming to me is that things that naturally warm our atmosphere from year to year, such as El Nino events, like the one that we had in 2016, they're starting to be beat out by years without them. So like 2019 was not an El Nino event, and illustrating how strong the human imposed warming signal is on natural climate variability. And Virginia is not immune to warming either. So this is a plot of data from Richmond from NOAA's Climate at a Glance portal. And in fact, the stripes that you see outlining the left of all my slides, they are the warming stripes for Virginia. And overall, Richmond specifically is warmed by almost 0.5 degrees Fahrenheit each decade, which is seen in that blue trend line. So here we're getting hotter and we're getting muggier as dew point temperatures rise. Heat waves are increasing. There are 6 more days above 95 now today than there were back in 1970. 160,000 people in Virginia are vulnerable to extreme heat, especially those under the age of 5 and over 65 and those living in poverty. And actually my student, Allison Grant, is exploring how historical housing policies such as redlining, or areas that were deemed hazardous to live and thus people could not get home loans, how they're disproportionately exposed to extreme urban heat in the summer, which is essentially affecting lower income and African-American communities more. And the impacts are far reaching than just warmer temperatures. So much like most of the US Northeast, we will see rainier days, but more as periods of intense rainfall over a short period of time, increasing inland flooding risk. And with sea levels rising, high tides will cause more coastal flooding, or what we call sunny day flooding. Tropical storms are also expected to get stronger as they are fueled by warmer water and cause even more flooding with storm surge on top of higher sea level. But maybe most importantly is the impact that climate change will have and is having on our health and how it disproportionately affects African Americans and lower income communities. So with more extreme heat days, heat-related illnesses will be up. Warmer air leads to more smog, which triggers asthma. Allergy season will be longer and more intense. Coastal flooding will make it harder for emergency services to reach people. Saltwater intrusion and increased runoff from heavier rains will pollute our water, making some of our drinking water and our seafood unsafe to drink and eat. And there will be an increase in mosquito and tick-borne illnesses. And as a fun fact, as a victim to dengue fever related to climate change, I can attest that that was not fun to get. So you can see why we call this a crisis. I just listed a few of the impacts, mostly as they pertain to Virginia, but the impacts are dire. So the Intergovernmental Panel on Climate Change, or IPCC, they have very carefully outlined the consequences from just a 1.5 degrees Celsius warming in temperature to a 2 degrees Celsius warming in temperature compared to pre-industrial times. So these reports, they're written by dozens of climate scientists, and they're very carefully peer-reviewed by hundreds more. So what is plotted here includes our monthly temperature change in the gray line, and then the estimated warming in the red line. And then this projects on different scenarios to keep our total warming from pre-industrial times to around 1.5 degrees Celsius. I should note that we have already warmed by more than 1 degree Celsius, which is almost 2 degrees Fahrenheit. And that our most ambitious goal is to stay within that 1.5 degrees C warming, even though the Paris Agreement first suggested a 2 degree C warming target. And I actually find the 1.5 degree C warming report depressing and alarming at the same time, because I know how hard it is going to be to meet that goal. And especially knowing how drastic those consequences will be, even from 0.5 degree Celsius warming difference, from 1.5 degrees to 2.5 degrees total, from more intense flooding and droughts to more species going to extinct, corals especially at my heart, to worse climate-related health impacts. But not to be too depressing, but right now, if no measures are taken, we're on track for a 3 to 5 degrees Celsius warming by 2100. That's an increase by about 5.4 to 9 degrees Fahrenheit. But let's look at what the main problem is and where all the carbon emissions are coming from, because we need to know how and where to cut back if we want to ultimately reach those warming targets. So our main source emissions by far is burning fossil fuels. If we break down those emissions globally, we can get a sense of where most of our emissions come from. Over 75% of our emissions, they are directly related to burning fossil fuels. The other 24% coming from agriculture and land use changes. A quarter comes directly from electricity and heat production, so the direct burning of coal, natural gas, and oil for electricity and heat. And then the rest is comprised of the industry, transportation, buildings, and other just being energy that's not directly associated with electricity or heat production. But maybe a little bit more relatable, let's just look at the US emissions. Half of our country's emissions comes from transportation and power or electricity. Then industry comprises about 22%, and then agriculture, commercial, and residential combined make up that last 20%. And here's a pie chart that I created from data from the US Energy and Information Administration for just Virginia's emissions. And you can see that transportation makes up almost 50% of our emissions alone. And then power makes up almost 1/3 of our emissions after transportation. So this brings me to the pandemic, where life was disrupted for everybody. Global economies shut down, people mostly stayed in confinement. General operations, they were reduced from businesses to institutions and governments. Many businesses actually either shut down or they provided their employees the option to telework. And governments mandated the stay-at-home orders that were largely followed. And I found this picture that someone took of Atlanta of no cars on the main interstate. And I was particularly fascinated with this after living in Atlanta for 4 years. And for any of you that have ever been to Atlanta, you know what I'm talking about. The traffic there is a nightmare. But this was actually something that we saw all over the country. And so plotted here is nationwide traffic data from INRIX that shows the decline in traffic volumes to over 40% in late March and early April. But then, of course, you can see this gradual rise back through May as things started to open up, and people were probably getting antsy from being home so long anyways that they started to come out of confinement. But the same trends have been reported all over the world in major economic countries. So the International Energy Agency reports that global average road transport activity fell by 50% of 2019 levels by end of March. You can see here in these plots from Berlin, London, Milan, New York, Paris, and Shanghai, where all the blue lines are the 2019 levels, and the red lines are the 2020 traffic levels. And there's that clear decrease as each of these cities and their countries went into confinement. Besides the carbon emissions from cars, there are other things that we care about that affect our health, such as carbon monoxide, nitrogen oxide, sulfur dioxide, hydrocarbons, and particulate matter. I just want to briefly focus on particulate matter and nitrogen oxides, or nitrogen dioxide, particularly NO2. So particulate matter are extremely fine material, so less than 2.5 microns. So to put that into perspective, the human hair is 50 to 70 microns. And it is well known that this affects human health, increasing the risk of stroke, heart disease, cancers. And in fact, almost 7 million people die each year because of air pollution. And what is more striking is that we found that areas with higher exposure to particulate matter have a higher mortality rate from COVID-19. And even here in the United States, counties with a COVID-19 death rate are 4 times higher than those with low pollution. And it's not even across the board. It affects lower income and African American communities the worst. Of course, the good news is that the air pollution can be reversed more quickly, as we've seen. So first, we saw the dramatic images of some of the most polluted cities from before and during the pandemic that showed significantly clearer air, really providing us a glimpse into what life might look like with fewer fossil fuels. So here's just one example from New Delhi, which is the world's most polluted city. And then the satellite measurements of the nitrogen dioxide, so one of those other tailpipe pollutants, they quickly emerged, starting with China. A recent study published that they estimated a 35% reduction in particulate matter and then a 60% reduction in nitrogen dioxide following the lockdown. I mean, you can see that clearly in this image where those cloud of those orange and reds, or the NO2 values around Beijing, virtually disappears. And then here's plots from Europe, from before and then during the confinement. So Madrid, Milan, and Rome, they saw decreases around 45%, and Paris as much as 54%, all coinciding with their strict quarantine measures. And so again, you can see this as those deep red colors, which have higher concentrations, they disappear in 2020. And NASA has even published NO2 values for the US Northeast here, showing about an average 30% drop. And you can see that the largest changes are around our major metropolitan cities, such as New York, Philadelphia, Baltimore, and Washington, DC. But of course, things are constantly evolving, and as restrictions ease, air pollution is returning just as fast as it improved during the confinement period. So this is an article that was just out last week in The Guardian, stating that air pollution in China is back to pre-COVID levels, and Europe is closely following. And if we look just here in Virginia, we too have been driving less. So I have to give a plug to my other student, Eden Rakes, who is trying to quantify the total amount of reduced emissions in the state of Virginia due to the mandated stay-at-home order. And so she compiled this data from the Virginia Department of Transportation, and the state as a whole has seen about a 40% reduction in traffic, which that's the black line in this plot. And interestingly, there's a sharper decline on weekends, highlighted by those gray bars in the plot, and most likely illustrates that people were staying home. And she's done a rough calculation in the amount of emissions that this saved, and it's on the order of removing about 1 million cars from the road for 1 year. But of course, as the state begins reopening, the traffic volumes are already starting to creep back up. And I even just looked right here at Fredericksburg and just at the section on Route 1, your campus during midweek. So removing that I-95 through traffic. And you can see a peak reduction about 45% in early to mid-April, which I've highlighted there in yellow. So people really were staying home during this time. And we can even see some improvements in our local air quality. So these are two plots that Dr. Jeremy Hoffman made. He's the chief scientist at the Science Museum of Virginia, and he provided me these that illustrate the changes in particulate matter and nitrogen dioxide near Bryan Park in Richmond. So all this data was provided by Virginia's Department of Environmental Quality. So these are plotted by averages by hour during weekdays, which is seen there on the x-axis of each of these plots. And the faint lines, those are the previous 4 years. And then the bold line is 2020, this year. And you can see for both of them, this two hump structure, particularly for the particulate matter and then the nitrogen dioxide, and where you get these increases around 6 a.m. and then 7 p.m. again, most likely coinciding with the rush hour traffic. So if we just look at the particulate matter, the plot on the left, in 2020, it appears to be quite a bit less than previous years. I will note, though, that this data is especially sensitive to rainfall, as that also scrubs the particulate matter out of the atmosphere, and that has not been considered here. But you can see one of the other faint lines on this plot that is only slightly higher than 2020 levels, but lower than those other previous years. And so that was 2019, which was a rainier year. So for nitrogen dioxide on the right, those last 4 years are remarkably similar in structure, with 2020 standing out from those previous years overall with lower values. So maybe not as drastic improvements as major cities, but of course, air quality here pre-COVID was better than some of those larger metropolitan cities. Okay, but how does this all relate to CO2 emissions and global climate change? So if you recall, our goal is that we really want to keep our global average temperatures to within 1 degree C warming to lessen the environmental, the ecological, the human health, and the economic impacts. To do so, we need to reduce our emissions by 7.5% every year. We'll let that sink in for a minute. 7.5% every year, at least for the next decade or until we reach net zero. There is precedent from previous major economic disruptions causing these small dips in carbon emissions. So this plots the rise in CO2 emissions in billions of tons of carbon, which is gigatons. And you can see small dips here from the Spanish flu, the Great Depression, the World Wars, the Soviet Union collapse, and the most recent one being the 2008 and 2009 financial crash, which that caused about a 1.3% dip in carbon emissions. And we expect that the drop this year will be the greatest drop since the Great Depression. The bad news is that once the crisis is over, emissions soar back up and usually higher than what they were before. So this is something that we need to stop from happening this time, but of course doing it in more of a responsible manner, prioritizing clean energy and spurring economic growth and jobs. So you can see our forecast here for 2020, which is plotted as that red dot. Many groups have already tried to predict where we'll end up at the end of this year, and estimates range anywhere from a 4 to 10% reduction. But those estimates are constantly changing. But either way, we do expect this to represent the largest annual drop in emissions ever recorded. And this is a hot topic. So in a paper just out in Nature, a premier peer-reviewed journal for the most cutting-edge science, a group estimated the total reduction for global emissions during the pandemic. And this is not easy to do because we do not have real-time CO2 emission data. So they had to deduce their values based on overall energy data available from all the top countries that are responsible for 97% of global emissions. And it's actually quite amazing how quickly they were able to put this all together. So they found an average 17% daily reduction, so a daily reduction in CO2 emissions compared to 2019 levels. And when plotted with the yearly rise, this looks quite like a steep drop in emissions. And if we zoom into it month by month, you can see the trend a little bit better. It's not constant because countries went into lockdowns at different times. And in fact, if you just look at country by country, at the peak of each of their lockdown, emission reductions were on the order of average of a 26% reduced. And at the time of the largest reduction in emissions in early April, we hit 2006 levels. They even break this down by energy sector. And overall, there was a 7.4% reduction in power sector, which is the electricity and the heat, 19% in industry, which is production of materials, and it's mostly based off coal consumption and steel production, 36% in surface transport, which includes everything on the roads, including national and international shipping, and 21% in public buildings and 60% in aviation. And then they saw a 2.8% increase in residential, which is of course not surprising with more people staying home. But what we need to consider is the total percent that each of these represent in total emissions. So for example, aviation or flights, both domestic and international, they represent the largest decrease percentage-wise at 60%. But since they only account for less than 3% of our global fossil fuel emissions, it did not have a significant effect on overall emission reductions. However, surface transport, meaning cars, trucks, everything driving on the road, they account for 20% of global fossil fuel emissions, and they saw a 36% decrease, thus actually having a real impact on total overall emission reductions. And so they estimate a 4 to 7% decrease in annual emissions for 2020, but note that it is hard to estimate as it depends on the duration of the confinement. And again, I have to reiterate that the emission reductions in this manner are not welcome. It really just provides a learning opportunity to discuss what types of measures could deliver the most significant long-term impact on emission reductions. But let me put this into context. This is a plot that illustrates the annual atmospheric growth of carbon dioxide in gigatons of carbon. So you can see that this is not a nice, smooth, linear increase that you see when we just plot the increase in concentration in parts per million. Rather, this illustrates year-to-year fluctuations in the growth of CO2 in our atmosphere. So keep in mind that emissions do steadily increase, but only about 45% of the CO2 that was created by burning of fossil fuels actually stays in our atmosphere. The rest is actually taken up by the ocean and plants, or like our biosphere. So the annual growth rate fluctuates quite a bit from natural influencers and actually masks the long-term human cause factor over short time periods. So just to give you an example, an extreme 10% drop in emissions in 2020 would equate to approximately 17 gigatons of carbon, and that is well within natural variability. So the influence of the natural carbon cycle by plants, soils, annual variations from temperature, humidity, soil moisture, as well as weather will most likely mask that short-term drop in emissions from COVID-19 pandemic, meaning that the missing emission reductions will probably not stand out on the short term. And with fossil fuels still being burned, atmospheric CO2 concentrations will still rise. We are still emitting CO2, and so it will still continue to accumulate in the atmosphere. So you can think of CO2 in the atmosphere as a bathtub of water, where the emissions are the faucet of the water coming into the tub. The lockdowns, they just mean that the tap has been turned down ever so slightly, that CO2 is still streaming into the bathtub, with only some leaking out of the bottom from natural carbon sinks. And actually, natural carbon sinks are the movement of carbon from the atmosphere to places like the ocean or the biosphere. They're very slow. So even if we did stop burning all fossil fuels today, a good bit of it will be removed in tens of years. But as more and more CO2 is removed, these natural sinks slow down. And so about 10% would remain in the atmosphere over tens of thousands of years. And unfortunately, just looking at the first 3 months of this year, seen as the black line in this plot, 2020 is already tracking to be one of the warmest, if not the warmest year on record. So meaning that even such sudden cuts in carbon emissions related to the coronavirus pandemic will not affect global average surface temperatures in the near future. And one thing to actually consider is that cleaner air can actually increase air temperatures because there's less aerosols for that sun to reflect back off. Okay, just to reiterate though, again, cutting emissions by cutting economic activity is not the solution, and it is nothing that we should cheer for. The suffering resulting from this pandemic, both in health and economic terms, that is something that we have to avoid as we move forward. And not only avoid, but help be part of the solution towards better health and more prosperous economies. But we can take this as a lesson that if we really implement systematic change from top down, we can make a difference. And I think the most promising are the reductions in emissions from surface transportation or traffic, both globally and locally here in Virginia. So we saw that this energy sector is responsive to policy change and economic shifts. Cities actually closed down their streets to traffic, making them pedestrian friendly. You know, we could shift development to more clustered communities around public transport. We could electrify the vehicles. School buses are a great example of this. But then secondly, we really need to see a wholesale shift to decarbonize our power sector. I think this will be important, especially as we rebuild our economy, as this has the potential to create jobs and save money over long term on energy costs. And lastly, I think this also highlights that we can't make this happen from individual action, as much as that makes me cringe to say that. The pandemic has demonstrated that it is the industry, that it's not personal choices that have the largest impact on the climate crisis. So even if we as individuals did everything we could to cut our carbon footprint, it would not be enough. But I don't want to belittle that effort, because every little bit does help. And I think more so that there's a lot of power for individual action, for initiating those grassroots movements to get those more systematic changes to happen from top down. And if the pandemic has taught anyone anything about climate change, it's the understanding of how to flatten a curve. So very similarly here, we can illustrate the importance and the urgency to implement climate protective measures, reducing our carbon emissions, and to keep those global temperatures below that 1.5 degree to 2 degrees Celsius warming, and avoiding the most catastrophic consequences of climate change. So I read an analogy that I really like that compared the two crises. The COVID-19 therapies, so ways to make people more comfortable while recovering from the disease, they are like our climate adaptations, are making our communities more resilient. Whereas the vaccine that scientists are feverishly trying to develop for COVID-19, that's like our net zero technologies and practices. And I really like this quote too from Bill McKinnon, who's a co-founder of 350.org. He said in a 60 Minutes interview, "If we flatten the carbon curve, then people might look back in 50 years at this time and thank us instead of curse us." So to just conclude and wrap up here, we saw dramatic improvement in air quality in a matter of weeks, illustrating how quickly we can turn around that situation by reducing fossil fuel emissions. Scientists found that day-to-day global emissions were down on average by 17% compared to 2019, and suggest that the annual emissions reductions will be anywhere from 4 to 8%. Now, the higher end is on par with what we need to reduce our emissions, but for every year for the next decade at least, to meet that IPCC 1.5 degrees C warming target. But of course, this is not the solution how to do that. We really need those systematic change driven by better policies to limit our warming and to reduce the impacts related to climate change. Now, I realize that this is going to be hard, as many local and state governments are struggling financially, being hit hard by the pandemic, especially as they would face high upfront costs to decarbonize the energy sector. And maybe even more so with our current national leader relaxing environmental standards. So I think it will be important to be creative in how we make this happen. And I'll have to end with that. I don't have the solution for that. And it will probably be dependent on each locality. But this is where we all need to come together and make it happen. So with that, I want to thank you all for watching, and thank you so much for your time. This is really definitely a unique way to give a presentation when I can't see a single one of you, but I trust that you're out there. Otherwise, I'm sure Jeremy probably would have let me know by now. And I always have to end on a happy note, which is my family and my two little precious boys who are 3 and 1 years old, who apparently were probably watching this. I don't know how long they made it. But again, thank you again, and I'm happy to entertain any questions now.
Fantastic. Yes, I do have some questions. Give me a second to pull these up. Okay, this is from alum Mike Faden. He is asking about the predictions for what could happen if and when we cross the 2 degrees Celsius threshold.
It's scary. And so we're already feeling the impacts from extreme weather events. So just the species going extinct, and as we just continue to keep climbing and climbing and climbing, everything just gets worse. You know, warmer temperatures, and then you have the related health effects that go with that, with the extreme heat days, and sea levels are going to rise, and you're going to have, you know, communities that are going to be completely displaced because of that, and storms are going to be getting stronger, tropical storms are getting stronger. So it's not pretty in terms of extreme events, in terms of species and the ecology, and even just the economy too, and just thinking about dealing with the consequence of people having to be displaced from, say, sea level, or just constant flooding. So it's everything that we're already feeling, and just then some.
Okay, I have one more question. This is also from Mike Faden. He was very enthusiastic. And I'm going to sum this up. So you meet somebody standing in an elevator, and you have an elevator speech for when they find out what you do, what they can do. Like, what's the one thing you should tell everyone that they can make a difference in their lives, quick, maybe not quickly or easily, but if they were to focus on one thing, what might that be to make a difference?
I would say talk about it. That is the one thing that is a problem, is that people in general do not talk about climate change enough. And you know, I had some things to equivalent with myself with the whole COVID situation, and just the more I heard about it, because I'm not an expert at it, and the more it sunk in, the more you see people doing things like wearing the mask. You're like, okay, let's do this. So the more we talk about it, the more we model it, then you're going to get other people that are going to start asking questions, and maybe start modeling that behavior. So that's why when I cringed about the whole individual action versus collective action, because I think, again, it's power. If you model that behavior and you talk about that behavior as an individual, you're going to get more people on board. And then second would be the advocacy. Do what you can to get out there. So I'm trying to be heavily involved in some local groups like Fossil Free Fredericksburg, for some of you that might know that organization here in town, and trying to move our cities and our states to commit to, you know, net zero emissions. So, you know, I would say talk about it, and then I would say get involved in some advocacy.
Cool. I had another question pop up from a parent, Chris Galen. He's asking for you to talk about your coral restoration research projects in Bonaire.
Yes, yes. So I am crossing my fingers that we can travel and do this again in next spring. So last spring was the first time that I ran this, and it's in partnership with the Scuba Shack here in town. And so we talk about climate change and how it affects particularly coral reefs, which are, you know, not going to fare well with these rising temperatures. And so part of this class is to instill hope to students, and so that they feel hopeful and that they can be part of the change. And so that's why we got involved with the coral restoration in Bonaire. So we go down there for 1 full week, and they actually do a coral restoration certificate. So we get on those reefs, and we learn how to, you know, do the little gardening of these corals, and we hang them on little trees and they grow, and then you transplant them out on the reef. So the students physically do that. So it involves scuba certification, which is a skill that they get. But it was a blast. I had the most fun teaching that ever, and the students really loved it.
Fantastic. Well, I think that was the last question that we have. Thank you, Pam, for joining us this evening. And thanks again to all of our viewers at home for joining us digitally for tonight's presentation. As a quick reminder, this presentation will be available for viewing here on the University of Mary Washington Alumni Facebook page and on the UMW YouTube channel starting sometime tomorrow. There you can watch this and the full catalog of Mary Talks. Though we don't yet have a date for our next Mary Talk, keep an eye out for an email communication later this summer for our next installment. Pam, thank you again, and to you and to our viewers, enjoy your evening, stay safe, and good night.
Good night.